Hi, hello everyone. So today we will work on the three-phase circuit. So there will be two experiments for today's level prac. So first is a three-phase circuit voltage current measurement, and the second part is about the three-phase power measurement. So regarding the experiment objective, when you have completed this unit, you will be able to solve balanced three-phase AC circuit connected in Y and delta configuration, and it demonstrates the difference between line and phase voltage. You will also be able to determine active, reactive, and apparent power, and establish the phase sequence of a three-phase AC power supply. You will use voltage and current measurements to verify the theory and calculation presented in the exercise. So experiment 1 is balance the three-phase circuit. So for this one, when you have completed this exercise, you will be able to distinguish between line and phase voltages in Y and delta connected AC circuit. Measured parameters in balanced resistive loads will be used to verify the circuit calculations. So now I will show you the platforms we will use today for the three-phase circuit level prac. So here, this module is a data acquisition module, and this is a power supply module, and this is a resistive load module. So we're going to use those modules today. So first, install the power supply, data acquisition module, and a resistive load module in the EMS workstation. So now they are properly installed already. Make sure that the main switch of the power supply is set to off position and the voltage knob is turned fully counterclockwise. Make sure that the power supply is connected to a three-phase receptacle. So now the power supply is connected, the knob is in the minimum position, so there's no voltage now. The light just indicates the power is connected properly. Make sure the data acquisition module is connected to a USB port of the computer. So this is a USB cable connected to the computer now already. And also connect the power supply to the data acquisition module. So you can see I have already connected the 24 volts AC output power to the data acquisition module. Start the data acquisition software. Open setup configuration ES16-1. So now the software is installed in this computer. Let's open the configuration file mentioned here in the document.
Actually, I don't know, maybe or whatever I think by the way. So the next thing you do will be to add the capacity. And you can make sure positive goes to that side, negative goes to that side, otherwise it will fall.
So now we need to open the ES. -1.
And what are you expecting this to look like? Okay, so let's see what happens. It doesn't go bang, it turns off, turns off, turns off, turns off.
Now I have opened the configuration file mentioned in the document. So you can see here, those are the three meters, E1, E2, and E3. So we will use those readings in the following experiment. we need to connect meter input E1, E2, and E3 to measure the line to neutral and then the line to line fixed voltages of the power supply shown in this figure. So you will see this document in the Learn GCU. Now I will connect the circuit by referring to this diagram.
That might be nice. The next best thing you can do is have it with another now it's kind of not top, so what you can do is bring it down a little bit, but then that kind of mucks all this stuff up. So anyway, just muck it around a bit. Just get it, I would say leave it like that, probably. Get all the two curses. That's actually a nice screenshot. You can see that got a ripple so it gives you a nice argument for making your prac sheet. Rather than you having to like draw it on later or just pull numbers up and then just show how they do it. Anyway, I'll be back in just a second. I'm just stuck with the bottom.
Now I have built the circuit. So here the voltage meter E1, E2, and E3 are measuring the voltage for each phase of the power supply, as you can see here. Then we need to turn on the main power supply and adjust the voltage knob to 100%. So the power supply is on, adjust it to 100%. Here this is 100%. As you can see, those numbers indicate the voltage percentage. So here is 100% now. Now we need to record the measured values, then turn off the power supply, determine the average values of the phase and the line voltages. Now let's look at the meter reading. So you can see meter E1, E2, and E3. Those are the three meter reading you should write down on your report. And calculate the average phase voltage E1 and E2 and E3 and the sum divided by 3.
Instead of coming all the way back down, we can about 36,000 charges up. Then when the voltage would cycle down to 0, to us it's still charged, so it slows
So now you have the reading for each phase voltage. Now we need to measure the line-to-line voltage. So we need to reconnect the voltage meter to measure the line-to-line voltage. So first turn off the voltage, make the voltage to minimum, and then reconnect the circuit.
So that's the brick wall. What was what we wanted to design? Yeah, but before that stage, when we were designing and choosing capacitance value, we had to calculate the capacitance with the more brick wall, not 12. So if we go back to again back to one sheet. Yeah, so you want that difference between maximum and minimum to be less than 2. So you know, it comes back to another point, but first of all, is that less than 2? No, it's a bit more. Okay. And remember what I was telling you on the other side is power supply is more than what you designed for. So what that probably means is everything needs to go up. So you can upsize it to go up a bit.
Now I have reconnected the circuit. So here for the voltage meter E1, it is measuring the voltage between phase 1 and phase 2. For voltage meter E2, it is measuring the line-to-line voltage between phase 2 and phase 3. For voltage meter 3, it is measuring phase 1 and phase 3. Let's still adjust the voltage knob to 100%.
I was seeing more ripple effect, so I went to a lot of the customer size. And you can even do the calculation if you want to see what do or not. Obviously there are markers associated with all of that, but you calculate how much you try to customer should balance how much time you actually spend on that. But I would recommend you show.
So now you can see voltage meter E1, E2, E3 are measuring the line-to-line voltage. So please keep a record of those reading in your report and then calculate the average line-to-line voltage. E12, which is E12 plus E23 plus E31 divided by 3. Now you have the readings for both the line-to-line voltage and the single phase voltage. So calculate the ratio of the average line to phase voltage. Is the ratio approximately equal to 1.73, which is square root 3? Answer this question in the report. Question 10. Set up the three-phase one connected resistive circuit shown in figure 6-6. Do not connect the neutral of the resistive load to the neutral of the power supply. Connect the meter input I1, I2, I3, E1, E2, and E3 as shown in the figure to measure the current and voltages. So now we need to build the circuit by referring to this diagram. So here for this table, it is telling us which voltage and frequency configuration we should select. So here we will select the voltage 240 and frequency 50 Hz because this is close to the Australian local network voltage. Now I will start rebuilding the circuit.
The next part is a little bit more involved. So if I move where that one came to 60. So keep track of which side is your positive end. The positive end connects the output to another resistor. Whichever side you chose. Yeah, same enough. Input options like anyone move the windows there. Don't be scared to blow up either, because we've got 50 minutes in the draw. And we just did a bit of earlier today. Oh, sorry, so you, oh yeah, where we are. The series goes through the positive with there. Yeah. Yeah, so it was exactly how you had it before. Just bring your full socket up. So, you have it before, so this is the positive leg. Yeah. Now, your resistance is not, your load resistance is not connected to the, oh wait, okay, so which one's the positive leg? So your load resistance does not connect to the positive leg of the car. Correct. So the load resistor, so that's also a problem with how we have it for. So load resistor basically means the on maybe this side. Yeah. That is the positive side of it. Positive side of the gas is going to come through the series of this stuff. Yeah. And then the series will step out to the negative of the gas. So that, yeah. And then this needs to go in parallel with that with the gas side wasting.
Now I have finished building the circuit. So here voltage current meter I1, I2 and I3 is in serial connection with the resistive load. Voltage meter E1, E2, E3 are in parallel connection with the resistor resistive load.
What level does that then up?
Here for the power supply, we are using the portal number 1, number 2, and number 3 as power source.
You have to, if you don't do enough to it beforehand, that will break.
So set the voltage meter, select the switch to the 4 to 5 position. Here it is in 4 to 5 position. So the purpose set to 4-5 position is using this voltage meter to measure the line-to-line voltage, because the power source 4, 5, 6, those are not working. So we are not using this meter. Instead, we are using the reading from the computer. Turn the power supply on. Now it is on. And adjust the voltage knob for the line-to-line voltage as given in the figure. Now the knob is in 100%. So we need to open the configuration file ES16-2 now. Let's open the ES16-2. Now we have opened the configuration for the voltage, both the voltage meter and the current meter. So you can see here the current meter has no reading yet because our resistor now is open circuit. So here for the resistors, there are multiple values as you can see being indicated here. So let's select the value close to the value as given in the table. So you can see here for the voltage 240 and frequency 50 Hz, the resistor value is 1200. So we select the one 1200. And then now, let's have a look at the readings. So here the voltage meter is measuring the voltage for each resistor, R1, R2, and R3. For the current, they are measuring the current going through each resistor. So please keep a recording of those readings. For question 12, compare the individual load voltages and the load current. Are they approximately equal, showing that the load is balanced? Question 13, calculate the average phase voltage for the values measured in step 15. So this should be in step 11. So here, using those voltage values, calculate their average value. Is the ratio of line-to-line value and the phase value approximately equal to square root 3? So here, because this power source is not working, so please consider the line-to-line voltage as 450, and then use the average value of the phase voltage to calculate to answer the question 14. Question 15. Connect the meter input I1 as shown by the dashed line in figure 6-6 to measure the neutral line current with the power supply neutral connected to the neutral of the Y-connected load. Open the configuration of file ES16-3. Turn on the power supply and record the value of current IN with voltage ES adjusted to the same value as in the previous step. So here we need to reconnect the current meter. So for the current meter E1, we connect it between the neutral points. Now we have connected the current meter I1, connect it between the neutral point of resistive load and the neutral point of the power source. Now let's look at the current meter readings. So here you can see the meter I1. Now this is measuring the current going through the neutral line. So is the neutral current equal to 0? You can take approximate values. Is this relatively very small compared with other two readings? So is it approximately 0? Question 17, using the results of step 15, calculate the active power consumed in each phase of the circuit and the total power consumed by the load. So in the previous steps, you have measured the voltage across each resistor, and you have also measured the current going through each resistor. Now calculate the power consumed by each resistor. Determine the phase current using the values measured in step 15. So for the phase For the phase current, previously you have measured the phase current for R1, R2, and R3. You can calculate the average value for the phase current. Calculate total power rate using the phase voltage and current and compare it with the result obtained in step 21. Are both values approximately the same? So here in the report, it mentioned the step 15. Actually, that should be step 11, because in the step 11 we measured the phase voltage and the phase current. Please be aware of this correction. Then turn off the power supply and set up the three-phase delta-connected resistive load, as shown in figure 6-7. Connect the meter input I1, I2, I3, E1, E2, E3 as shown in the figure to measure the current and voltage. So we will rebuild the circuit by referring to this diagram. And now we have the circuit for the delta connection of resistive load. For each current meter, the current meter is measuring the phase current for R1, R2, and R3. For the voltage meter is measuring the voltage across R1, R2, and R3. Regarding the resistor values, we will select 1200 ohm as given in the table. So we are using the configuration voltage 240, frequency 50 Hz. Turn on the power supply, adjust the knob for the line-to-line voltage as given in figure 6-7. Open configuration file ES616-4, measure the circuit voltage and current. So here for the voltage, we still adjust it to the 100%. And then let's look at the meter readings. Now you can see we have the voltage meter readings and current meter readings. So here, please keep a record of the voltage readings and current readings. So here you can see for the voltage, if you refer to the circuit, you can see the voltage is actually the line-to-line voltage. And the current is a single phase current. Question 21, compare the individual load voltages and load currents. Are they approximately equal? Show that the load is balanced. 22, calculate the average phase current from the the values measured in the previous step 20. Calculate the average phase current. So now we have measured the voltage and current values for three-phase circuit. Please finish the questions using the recorded data, and also finish the review questions in the final part of experiment 1. Now we work on experiment 2, three-phase power measurement. The exercise objective is, when you have completed this exercise, you will be able to calculate active, reactive, and apparent power in balanced Y or delta connected three-phase circuit. You will know how to use a power meter to measure power in single-phase circuits. You will also know how to measure power in 3- and 4-wire three-phase systems. Now in this section, you will set up the equipment to measure power in 4-wire three-phase circuit. So first, install the power supply, data acquisition module, revisit the load and capacitive load module in the EMS workstation. So now we already have the power supply module, data acquisition. This is the capacitive load module, and this is the resistive load module. Make sure that the main switch of the power supply is set to the off. Now the power supply is off. The knob is in the minimum position, and the voltage control knob is turned fully counterclockwise. Set the voltmeter selector switch to the photo 5 position. Then make sure that the power supply is connected to a 3-phase wall receptacle. Make sure that the data acquisition module is connected to USB port to the computer. So now the data acquisition module is connected to the computer already. Connect the power input of the data acquisition module to the 24 volts AC output of the power supply is already connected. Power supply to the data acquisition module. Set the 24 volts AC power switch to the on position. It's already on. Start the data acquisition software. Now I will start the data acquisition software in the computer and open the configuration file ES16-6A. Now we have select the data configuration file ES16-6A. And now we need to set up the circuit. Now we need to set up the circuit by referring to the diagram given in the document. So as you can see here, we need to connect the circuit by referring to same as this diagram. Now I have finalized building the circuit. As you can see here, the power from each phase of the power source, the power go to the current meter. So via the current meter is in serial connection with the load. So from the current meter, the electricity goes to the load. The load is includes resistive load and capacitive load. They connected together in serial, and then the electricity back to the neutral point of the power source. So for the voltage meters, the voltage meter is in serial connection for each load. So as you can see here, one terminal is connecting to the current meter, another terminal is connecting to the neutral point of the power source. So in this way, each current meter is measuring the current in each phase, and each voltage meter is measuring the voltage for each phase. So now we need to configure the resistive load and capacitive load value by referring to the table here. So as you can see, the table is given here, telling you the resistor and the capacitor value. Because here our voltage local network voltage level is 240 volts and frequency is 50 Hz. So we select the final group. So now here I will zoom in a bit. So you can see here on the panel, it has 3 parallel connected resistors for the resistive load. So we need to connect those 3 resistors in parallel, put all of them on, so their total resistance value is approximately 686 as required in the table. At the same time, for this capacitive load, it also has 3 capacitors in parallel connection here. So because it's via the parallel connection, we cannot exactly get the 960 ohm capacitive load. So we will use the parallel connection of the 2 of the capacitors to approximately get 800 ohm resistance. Now we have made the necessary switch settings on the resistive load and capacitive load modules in order to obtain the resistance and capacitive reactance values required. So measuring the total power in 4-wire 3-phase circuit. In this section, you will solve the circuit you set up in the previous section by calculating the active, reactive, and apparent power values in each phase of the circuit. So by referring to the circuit as given here in the report, do the calculation first. You will measure the circuit voltage, current, and power values and confirm that the measured circuit parameters are equal to the calculated circuit parameters. You will then unbalance the 3-phase circuit by modifying the impedance in one phase of the circuit and solve the resulting unbalanced 3-phase circuit. Finally, you will measure the total active, reactive, and apparent power values in the circuit and verify that the measured circuit parameters are equal to the calculated circuit parameters. thus confirming that the total power in both balanced and unbalanced 4-wire 3-phase circuits can be measured using 3 power meters. So now for question 7, solve the circuit in figure 14 to determine the following parameters: the active power, reactive power, and apparent power in each phase of the circuit, as well as the total active power, total reactive power, and total apparent power in the circuit. Then question 8, turn on the main power supply and set the voltage knob so that the AC power source voltage is equal to the nominal voltage of the AC power network. Do not change the setting of the voltage control knob until the end of the exercise. Measure and record below the voltages and currents in the circuit of the figure 14, as well as active power, reactive power, and apparent power in each phase of the circuit, and then turn off the power supply. Now let's turn on the power. Now we have adjusted the knob so that we can have the power voltage as required in the table. It means each phase, for each phase voltage, it is 240 roughly. And now we need to make a record for the voltage and current measurements. So now in this reading, as you can see here, we have E1, E2, E3. So those first 3 are the voltage meters measuring the phase current in the circuit, phase voltage in the circuit. And for the meter I1, I2, and I3, those are the 3 current meters measuring the current value in the circuit. So for the power, the last row of power meters, PQS1, PQS2, and PQS3, so those 3 meters are measuring the power within the circuit. So currently, those are the active power values. As you can see here, P unit is volts, P unit volts, P unit volts. And now, after you write down the active power value, I will adjust the setting to obtain the reactive power value. Now, those are the values for the reactive power consumption now. As you can see, those are negative reactive power values. And finally, we can also obtain the apparent power values. So now I adjust the settings of the meters, power meters, so you can have the readings of apparent power values. So here, for each active power, reactive, and apparent power, this meter 13 is corresponding to E1, I1. This meter M14 is corresponding to E2, I2. And the third one corresponding to E3, I3. Now you have the voltage and current measurements as well as the power measurements. So question 9, compare the voltage, current, and power, including active, reactive, and apparent power values measured in the previous step with the parameter values calculated in step 7. Are all values approximately equal? Open setup configuration file ES167A. This file adds a meter in the metering window that indicates the total power in the three-phase circuit. Now, let's select another data acquisition configuration file. So this configuration is the configuration file ES16-7A. So as you can see here, we are having one extra power meter. Turn on the power supply. The power supply is already on. Measure and record successively the total active power, total reactive power, and total apparent power in the circuit using the total power meter set in the previous step. Now, you can see here, this is a meter. This meter, the third meter, the additional meter is measuring PS1, PQS1 plus PQS2 plus PQS3. So this is measuring the total. Now this is a total active power. And this is a total reactive power being measured here. I change again. So now this is the total apparent power being measured. So you need to keep a record for the total power values. Compare the total power values you just measured with the total active power, total reactive power, and total apparent power calculated in step 7. Are all values approximately equal? Now, step 12, modify the switch settings on the resistive load and capacitive load modules in the circuit of 14 in order to obtain the resistance and capacitive reactance values indicated in table 6-1. Due to this modification, the three-phase load is now unbalanced, i.e. the first phase of the circuit has a different impedance from that of the second and third phase. So here I would like to emphasize in your calculation, in the previous measurement, in the calculation, because I'm using parallel connection 2,400 ohm and 1,200 ohm capacitive load. So here, for the value in the table, this value is 800. In your calculation, use 800 instead of 960. And now we need to change the configuration. So here you can see for the new configuration, those are still 800. So for the X1, the first reactance, we need to use this value, the 2400 ohm reactance. Now in this circuit, for R1, we need to change it to 1200. For R2 and R3, we keep it as 686. For the capacitors, the first capacitor, we change it to 2400. For the capacitor 2 and 3, we still use the 800 ohm. Those are the values, current values in the setup. Solve the circuit in figure 6-40 using the resistance and capacitive reactance values indicated in table 6-1 to determine the following parameters: the total active power, total reactive power, and the total apparent power. You need to manually calculate those power values. Turn on the power supply. The power supply is turned on. Successfully measure and record the active power, reactive power, and apparent power in the circuit using the total power meter you set up before, and turn off the power supply after finish. Now let's look at the meter values. So now, as you can see here, this meter is measuring the total active power consumption in the circuit under the unbalanced load scenario. So here, this is the total active power consumption. It actually equals to the sum for the previous 3 meters. You need to keep a record of this active power. Now I adjust. We have the reactive power total values. You need to keep a record of the total reactive power value as shown here. And then I adjust again. So this is the total apparent power values. Compare the total active power, total reactive power, and the total apparent power measured in the previous step with the total power values calculated in step 13. Are all values approximately equal? Then, do the circuit measurements performed in this section confirm that the total power in both balanced and unbalanced 4-wire three-phase circuits can be measured using 3-phase power meters? Now we need to conduct measuring the total power in 3-wire 3-phase circuit in the Y configuration. In this section, you will set up a balanced 3-wire Y-connected 3-phase circuit. You will measure the total active, reactive, and apparent power values in the circuit using the 2-voltmeter method and verify that the measured power values are equal to the calculated power values, thus confirming that the 2-voltmeter method of power measurement works for measuring the total power in balanced and 3-phase 3-wire circuits. Set up the circuit shown in figure 6.15. Now we need to set up the circuit by referring to this diagram. As you can see here, we have 2 voltage meters and 2 current meters. Now I have finished connecting the circuit. So as you can see here, for the voltage meter, for the current meter, we are using 2 current meters. Current meter 1 and current meter 2. current meter 1 and current meter 2. So for the first current meter, the electricity from the power source go to the current meter I1, and then from the I1 connecting to the load 1, including resistive load and capacitive load. For the voltage meter I1, it is measuring the voltage for the line-to-line voltage between phase 1 and phase 2. So for the second current meter, the electricity comes from the third phase 3 of the electricity, and then after the current meter, the electricity goes to resistive load 3 and capacitive load 3. They are in parallel, they are in serial connection. For the voltage meter E2, it is measuring the line-to-line voltage between phase 2 and phase 3, as you can see here, phase 2 and phase 3. So now we need to make the necessary switch settings on the resistive load and capacitive load module in order to obtain the value as given in the table. So here for the voltage, because our local network is 240, we're using this group of data. Frequency is 50 Hz. For the resistors, the value approximately 686 ohm. So for the capacitors, the capacitive reactance is not 960, it is 800 now. This is because of the modules available, the values available for this module. We can only have 800. So please be aware using this value. And now we need to open the setup configuration file ES16-8A. So now we have opened the configuration file 16-8A. Now we need to turn on the power supply here and make a recording of the data reading. So now we have the data reading for E1, E2, I1, and I2. Also for the power rate meters, we have the PQS1, PQS2. So this is the power readings corresponding to E1, I1. This is the power readings corresponding to E2, I2. So now you need, for question 19, successfully measure and record the total active power, total reactive power, and total apparent power in the circuit. Use the meter you have set up for total power measurement, then of the power supply. So here this is the total, this meter is telling us, it's showing the total real power consumption now. It equals to, you can see, the sum of the previous two values. And now we can change to reactive power values. So this total power, reactive power, is measuring this is a sum for all the previous two meters. You need to keep a record for this reactive power. And for the total apparent power, So this is a total apparent power for the circuit. So you need to keep a record for the total apparent power. Compare the total active power, total reactive power, and the total apparent power measured in the previous step with the total power values calculated in step 7. Are all values approximately equal? Then do the circuit measurements performed in this section confirm that the 2 voltmeter method of power measurement can be used to measure the total power in balanced 3-wire Y-connected 3-phase circuits? Now this is the end of our experiment 2. Please keep a record of all the data you collected, put them in the report, finalize the report, and answer the review questions as well. Then submit your finalized report in the LearnTCU system. Thank you.